Okay. So in this lesson, we will recognize and describe the different types of discontinuities. Discuss, this is important, you guys will need this for the AP test, the formal definition of continuity for calculus. And then you guys will learn to tell me whether or not something is continuous at a certain point. You guys will learn what that means. So the 1.10 part of this lesson is the types of discontinuities. So we're going to start with that first. So you guys have a graph. Or sorry, you guys have a box that looks like this. Okay. I have way too many tabs open, guys. Hold on, sorry. Do I sound really old when I say that? All right. So we say a function is continuous if there are no interruptions in the graph. Okay, I'm going to age myself right now. You guys are all born pretty much in 08, right? Or 09? Or no, sorry. No 09s in here. Either 07 or 08, correct? Okay. I took calculus in the spring semester of 2009, my second semester of college. Okay? And my teacher, my professor, the homie, he gave us this exact same definition. Okay? If you can draw a graph without lifting your pencil, it's continuous. So if you guys agree, if I draw this graph, I can successfully draw this graph without lifting my pencil. Okay? But right here, what does this graph have right here that's not actually drawn in? An asymptote. So if I want to draw this graph, I could draw this part, but you guys agree I'd have to lift my pencil up to get to the top, right? So that means that this graph is discontinuous. And the reason why is because it has an asymptote, a vertical asymptote specifically, okay? So this is discontinuous, this graph would be continuous. Specifically, it's discontinuous, it looks like at 0, okay? Cool? Hold on. I love technology. There we go. So we have 3 types of discontinuities. Well, what is that? It's a hole. If a graph has a hole, that means it's discontinuous at that value. Okay? Now, for the AP exam, sometimes they will classify these in a specific way. It won't say hole, it will say that the graph has what's called a removable discontinuity. And the reason why it's called removable is because right now there's a hole right here, right? And that's bad. But do you guys agree that I could just tell you guys, well, actually, do you guys agree there's a hole at 2, 3? I could say, actually, even though it's not there, that is there. And then I could do this. Is there a hole anymore? I removed it. That's what that means. If there's a hole, that means you could fill it in if you're told to. That's what it means by removable, okay? I'm going to erase that so that way you guys still see the hole there. Okay. What's the middle one? What's that red line? Specifically, what type? Vertical asymptote, good. So vertical asymptote we can abbreviate as VA. So unfortunately, unlike the hole, I can't remove it. So this is what we'd classify as non-removable. Okay, this last one. This looks like a linear function on this side. This kind of looks like a parabola, right? You're good. You're good. Do you guys see there's a gap right there? This is called a jump. Okay? When the values, there's a gap for piecewise functions, and you just have to you have to jump down or up to the next value. This is a jump. This is also non-removable. Questions? Okay, so you guys have an example. First example we're going to do is you guys have a graph that looks like it has holes and asymptotes and things happening. Okay, so what you're basically looking for, guys, is what you guys just talked about with me. Does there appear to be any jumps, any asymptotes, or any holes? And if there are, we want to say what they are. Okay, so let's start on the very left side of the graph. So at -3, it looks like we have a solid point, right? Then the graph is constant up to this point where there's a hole, but we wouldn't actually classify that as a hole because right there, it then continues down to here and then goes up. Does that make sense? So what is actually happening there? There's a jump. Good. So all I want you guys to do for your homework on this type of problem too is just at x equals -1, there's a jump. And that's all you have to say. Where's the next discontinuity? At 1? X is equal to +1. What's happening there? Vertical asymptote. Good. Where is the next one? 3? What's happening there? There's a hole. Good. Anywhere else? 5. Good. What's happening there? Hole. Okay. Just to practice, which is the only type of discontinuity we could say is removable? No, what type though? Holes. Good. So you can label this as removable. And then these ones are obviously non-removable. For the sake of this assignment, you don't have to classify them this way. I just want you guys to know what does a hole look like, what does a jump look like, what does a vertical asymptote look like. Okay, what's up?
Number 3, if you fill in the hole, wouldn't it cause an error or like?
Yes.
So how would that be removable?
But in general, a hole is what we call removable. Because
Oh.
what if I didn't put that point there instead? What if I just slid it up, boop, put it there?
You can do it.
We can do whatever we want. I made this graph on Desmos. Okay, everyone good? Okay. Now, we can look at it from a graph, but we can also look at it from a function. So we're going to bring back either good or bad memories right now from pre-cal or honors. Describe any discontinuities and where they are located. Okay, I know it's been a while since we've done problems like this, but what is this problem screaming at you guys to do first? Factor, good. Can I cancel the x squareds? Can I cancel the x's? No, good. What is the top factor to you guys? X minus 6, x minus 2, good. What about the bottom? Good. Now, I know you guys are probably noticing something right now, right? And you guys know what I'm talking about? Oh my goodness, oh my goodness. But at this moment, before you start classifying them, remember, we're never allowed to divide by what? 0. So immediately we have a discontinuity right here, and we have a discontinuity right here, because what makes the inside of this parentheses 0? -5. And what makes the inside of this parentheses 0? So we have two discontinuities. Is it a hole? Is it an asymptote? Or is it a jump? So we have to figure that out, okay? So I'm going to say that the discontinuities, this is really hard to spell. So if you guys spell it wrong, that's okay. We have a discontinuity at x is equal to -5 and x is equal to 2, but I want us to classify them. Okay. What's the thing that I notice, and I know you guys notice? X minus 2's cancel. So do you guys remember what that means in the graph? Very good. You guys are so smart. There's a hole. Good. So that means that x equals 2, we have a hole. This doesn't cancel though, right? So what does that mean about our graph? Vertical asymptote. Good. That's it. Questions? All right, let's make it more difficult. Can I do anything to the top right now? But the bottom, guys, it does factor. Does anybody see how it factors? Good. X squared plus 1, x squared minus 1. Good. Now, we don't have a formula for squared plus, but we do have a formula for squared minus, right? This also factors again. So I'm left with x plus 1 all over x squared plus 1. This guy right here factors to what? X plus 1, x minus 1. Good. Okay. I've said this already. I forget which lesson, but this right here, if I were to try to solve this, do you guys agree I could set this part equal to 0 and solve? You guys follow me? If I were to subtract 1 from both sides, that would make this negative 1. And if I square root that, what does that mean about my answers? Are we allowed to take the square root of a negative? That means the answers are what? Imaginary. In this class, we will deal with no i's. No imaginary numbers exist in this class. Okay, so you guys learn them. You guys are like, then why did we learn them? For later. Not in this class, though. Okay, so this right here, I can just leave alone. But notice that this and this are the same, right? So what happens to those? Cancel. Does this cancel? No. So we have discontinuities where? X is equal to negative 1 and x is equal to positive 1. Do you guys agree that this is the negative 1? 1, right? What is that? A whole? And the x minus 1 is a vertical asymptote? Is everybody good so far?
Like, how did that, when we cancel negative 1, then that makes it into a whole, but you got like x squared plus 1, and you put negative 1 into there, would that be also be a b?
Negative 1 squared is 1. 1 plus 1 gives me 2.
Oh, so it is.
This will never be 0. Unless you throw in imaginaries. We're not going to use our imagination today.
Not right now.
Not right now. All right, you guys ready for part C? You sure? All right, do one of these before we start. This one's a lot of work. All right. You guys love the trig graphs, right? We love them so much. Remember, some of them had asymptotes. And tangent was one of them. Okay? So, let's say that we don't remember what the asymptotes are here. Okay? Do you guys remember there was another way I could write tangent? Tangent is the same thing as what over what? Sine over cosine. Because then, check this out. I can rewrite this as the sine of 2x divided by the cosine of 2x. And do you guys agree that we're never allowed to divide by 0, right? So I just need to figure out what would make the bottom equal to 0. When is cosine of 2x equal to 0? Okay? Now, you guys did have a problem kind of like this when you guys did your pre-calc review packet. Okay? Now, I know it's 2x, but what I'm going to do first is I'm going to pretend like it's just x. Because then I can deal with the 2x part of this later. So I want to know when cosine of x is equal to 0. So if I have my fancy schmancy unit circle, is cosine x or y? X. So on the unit circle, x is 0 right there and right there. You guys follow me? What angle is this at the very top? Pi over 2. And what angle is this down below? 3 pi over 2. Okay? Now, do you guys agree that I could go around and around and around and around? And don't hate me, I know I'm recording this, but There's part of the directions. I got excited. I forgot to give you guys part of the directions. That part's important. Okay. So this is pi over 2, right? This is 3 pi over 2. If I went around here, that would be 2 pi, right? What angle would it be if I kept going? What angle would it be if I went to 2 pi and then went another pi over 2? 5 pi over 2? And then what would this be? 7 pi over 2? And then this would be 9 pi over 2. And then this would be 11 pi over 2. And I'm going to stop right there. Okay? So this is how we're going to answer this question. Cosine of x is equal to 0 when x is equal to pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, and so on. But they gave us this restriction, right? So what we need to do is, remember, we're also not solving for x, we're solving for 2x. So if these are the answers for x, I need to substitute 2x into here and figure out when does 2x equal this? When does 2x equal this? When does 2x equal that? Does that make sense? And the answers have to be, bless you, less than 2 pi. So once I've surpassed 2 pi, I can stop. So this is what we're going to do. 2x is equal to pi over 2. How would I solve for that? Divide by 2. Now, this is a fraction over here, right? You guys agree dividing by 2 is the same thing as multiplying by 1/2? So that means that x is actually equal to pi over 4. Okay? And then we can do the same thing for the other ones. 2x is equal to 3 pi over 2. If I divide both sides by 2, that means x is equal to 3 pi over 4. You guys follow me? Now, do you guys see all I'm basically doing is I'm taking the answers and then changing the 2 on the bottom to a 4? So this would be, the next one would be 5 pi over 4. This next one would be 7 pi over 4. 7 pi over 4, do you guys remember, is in this quadrant right here? So if I went again, if I did the next one, 9 pi over 4, guys, is actually up here. That's bigger than 2 pi. So do I have to include that one? No. So the 4 answers I'm going to pick are x is equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Now, these are when x is 0 on the bottom, correct? What does that mean about the graph if x is 0 on the bottom? Vertical asymptotes, good. These are all vertical asymptotes. The trig ones are tough. But do you guys agree, like, it didn't require that crazy of unit circle knowledge to do this problem, right? You just had to remember when cosine was 0. That was it. Okay. So that's 1.10. Now let's do 1.11. Remember how I told you guys it'd be good to get those tiny little sticky notes for your notebooks? This is, if you guys do have any sticky notes, this is something I definitely would sticky note because you guys need this one. Okay. For a function to be continuous at a point x is equal to c, the following three conditions must be met. First thing is, f of c is defined. If it's not defined, think about it, that means it could be a hole. So there can't be a hole there if it's going to be continuous. Okay? The next thing that has to be true is that the limit as x approaches c of f of x exists. Now, you guys just had a 3-day weekend where you guys may not have done any calculus, and that's okay. But what does it mean for the limit to exist? The left side and right side limit must be the same. Good job. So that means that the limit, that the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x. And in this case, in case you guys are confused, c is just a number. It could be 2, it could be 1, it could be 5. Now here's the part that the students last year was my first year teaching this, when they were asked to do a problem where they had to like confirm this, a lot of them forgot this step, okay? But you have to show that's defined, make sure the limits match. The last thing is these must be equal. F of c has to be the same thing as the limit as x approaches c of f of x. Now you're probably thinking like, that's kind of silly. Why is that true? You don't have to draw this, you can just watch. Let's say we have a function, guys, like this. Is f of c defined? Is there a point at x is equal to c? Yes. Does the limit exist? Is the limit from the left the same as the limit from the right? Yes, but are these hole and the point the same? So this would be discontinuous. Okay, does that make sense? This is why this should not be there if it's continuous. It should be like that. Okay? All right. This is you guys don't understand this right now. This is super important for our class. So what's the only classification we haven't talked about yet? We've talked about asymptotes. We've talked about holes. What's the other one we haven't talked about yet? Jumps. Jumps will typically happen when we have a piecewise function, okay? So, state whether f of x is continuous at x is equal to -1 and x is equal to 2. Justify your answers. All right, we have 15 minutes. You guys think we can do it? Yeah. Aiden think we can do it? Yeah. Okay. F of x is equal to x squared minus 2x plus 1 when x is less than -1. X plus 2 if -1 is less than or equal to x, which is less than 2. And then 2 to the x when x is greater than or equal to 2. Okay, so we're going to start with -1. So I'm going to call this part A. Now, I'm not trying to trick you guys. What is the first thing that you have to show that for it to be continuous? What does step 1 say in your notes? F of C is defined. So check this out. C in this case is -1. Look at your inequalities. Are one of the inequalities equal to for -1? Now, do you guys see how this one's less than and then this one's greater than because it's facing the x? Let's say if they're both not underlined, that means it's not defined. Okay, because that could happen sometimes to trick you. So it is defined because, am I allowed to plug in -1 into here? Yes, because that's what that says. Okay, so this is how I want you guys to write it. Step 1. Is f of -1 defined, question mark? Yes. And if it is, the last step is you have to show the limit is equal to the function value. So right now, while we're here, let's go ahead and plug it in. Okay? So f of -1 is equal to just -1 plus 2, and that's just 1. What's step 2? The limit exists. So you have to show the left's limit is the same thing as the right. Okay? So step 2, the limit as x approaches -1 of f of x exists, question mark. So, I'm going to use a different color. The limit as x approaches -1 from the left of f of x is equal to, which piece am I going to plug that into if it's the left side? Top, middle, or bottom? Top. Because if this is the left side, does that make sense? It's less. You guys follow me? Okay. So if I plug this in, it'd be -1 squared minus 2 times -1 plus 1. This would be a no calculator question, guys, so be careful. When you square negative, it becomes positive. So 1 plus 2, because the negatives cancel, plus 1. What does that give me? 4. Then the limit as x approaches -1 to the right of f of x, which piece do I plug that into? What? The middle? So it's just going to be -1 plus 2, which is just 1. Abel, what does that mean? The limit does not exist, which means is this continuous at -1? It's discontinuous at -1. Now, what type? Do you guys want to graph this? Absolutely not. This would be what type of function? This is squared. Quadratic. And then this would be a line. Do you guys want to graph that by hand? No. Okay. Second semester, we will do some problems where you have to graph these by hand first to do the problem. Those are fun. But because of this, does that make sense that we're jumping from 4 to 1? Because the values are different. So therefore, the limit as x approaches -1 of f of x does not exist. So therefore, f of x is, let's just say has a jump discontinuity at x is equal to -1. Okay, we're not going to finish this, but let's do part B. I'm going to scroll up real quick just to copy the function. You guys don't have to because it's in front of you. Any questions? Are you guys okay? You're okay? All right. So we're going to do the same process, but for 2 now. So step 1, guys, you guys agree would be to show that f of 2 exists? Does f of 2 exist? It does. Which one will I plug it into? Bottom, good. So f of 2 is equal to 2 squared, which is 4. This one's faster because we don't have a quadratic to plug it into. Okay. You guys with me? All right. Left side of limit. The limit as x approaches 2 from the left of f of x is equal to, which one will I plug it into? The middle? So that's just going to be, you guys agree, 2 plus 2? Hey, that's 4. What about the right side limit? Top, middle, or bottom? Bottom? Hey, that's 4. Hey, what do you guys notice? They're the same. So what does that mean about the limit? It does exist. So, therefore, the limit as x approaches 2 of f of x is equal to 4. So it does exist. Okay, here comes the easy part. What does step 3 say? What does your note say? Yeah, f of c has to be the same thing as the limit, right? What was f of c? What was our limit? What does that mean? Is it continuous? Absolutely. So you just have to say f of 2 is equal to, you already did the work for it, the limit as x approaches 2 of f of x, check. You just have to say that, okay? So your conclusion is this continuous at x equals 2? Yes. So, therefore, the limit as x approaches 2 of f of x is equal to f of 2. So, f of x is continuous. I'm running out of space. At x equals 2. Okay. I don't know if I had a lot of coffee or something last year, but like last year I did like 3 more problems in one day. I don't know if it was a block period or not because I'd have to go back to the calendar. But like I did this and I did an A and a B and then I did this and did A in the same day. I don't know. But we only have 4 minutes left. Okay. So here's what's going to happen. I already gave you guys your homework, right? This homework is not very long. You guys have most of the information. Let me turn this off.